Welcome to this session here on forest health, critical global issues in the 21st century. This is the subplenary session of Division 7, Forest Health, one of IUFRO's 9 science divisions. And I'm Eki Brockerhoff. I'm with SCION, the New Zealand Forest Research Institute, and I'll be moderating this session. It's my pleasure to introduce the first speaker, the first of two, Andrea Battisti. He's a professor of entomology at the University of Padova in Italy and has been since 2002. Previously, he was assistant professor and associate professor. His role there brought him back to where he obtained a master in forest science in 1982 before he received a PhD in entomology from the University of Bologna in 1987. In his role as professor, he's supervised 28 students, of whom many are now academics in entomology and other fields. He's published well over 100 papers in peer-reviewed journals, including many influential papers on subjects such as climate change impacts on forest insects. Andrea has also been very active in IUFRO. Currently, he's the coordinator of the working party entitled Integrated Management of Forest Defoliating Insects. He's also organized several conferences of IUFRO and was very much involved with some international congresses of entomology. And in fact, he was the organizer of the very first IUFRO conference I attended in 1995 in Italy, which impressed me very much. It was a wonderful meeting, and I think it got me hooked on IUFRO, so we do have a special connection. And it is my pleasure to introduce Andrea, and the title of his talk is Forest Insect Invasions, the Role of Global Change. Andrea.
Okay, so I will wait. Thank you very much, Eki, for the introduction. Thank you to you all for being here. As the presentation will start, I can start. No, it doesn't go. No. I can talk.
Do you want to slide? I can talk without slides. Well, I'm sure it will work in a second, but do you want to start just some background or whatever? Can you do that?
Yeah.
It won't be long.
Yeah.
You'll get a few extra minutes.
Oh, no. So I will start in any case to save time. So then problem will be fixed probably. Yeah. So I will talk about forest insect invasions, and I will use a double approach. The first approach, it will be addressed by the trade and the travel, which means transportation of organisms. The second would be climate change and how climate change is affecting the introduction of invasive species. And I will add something else at the end, other factors that could explain better how invasion can be explained in general. Okay, so that's perfect. So this I have done already. I will use material from the IUFRO Task Force on Forest Biological Invasions. There were many, many talks in these days from this task force. And there is a special issue in biological invasions just published with a lot of interesting contribution. I will use also other literature, and I will refer to the work done in my group in Padua. So first of all, the forest is a very general distribution of the forest. In the upper panel, very well known. The second panel is kind of distribution of biodiversity. This is kind of distribution of ant biodiversity, which is kind of proxy for insect biodiversity. And there is kind of geographic pattern when you combine with a general pattern of trade, which is identified by the red. The more intense the red, the higher is the trade. You can easily see that there is not a good match about location of the forest, location of biodiversity, and trade. And that is where most problem comes from. So, in a very recent paper in Nature Communication, where the diversity of the invasive organisms have been plotted for different number of taxa. Here I put plants and insects. We can easily see that the distribution of these invasive species, they match very well with the amount of trade going to different geographic areas. And that is the major explanation for the process of the biological invasion. I took this example from trees, shrubs, from Reimaneke. This is a book in forest ecology just published, where they used kind of known exchange between geographic areas to explain how many species of forest trees and shrubs they were moved from one geographic area to the other. And the network of the arrows is very complex, and mainly the thickness of the arrow indicates that the number of species moved from one area to the other is very different. This is just an example. We don't have such a figure for insects, but we will discuss soon what happens for insects. So what is the main outcome of this scheme is that there is asymmetry in the exchange. Different geographic area, they don't exchange the same number of species. There is a big difference into intentional and non-intentional exchange. Many plants, for example, they were intentionally taken from other non-native areas, whereas, for example, this is not the same for insects that are mainly unintentionally taken outside of the native range. And this has consequences. I mean, the movement of plants has consequences on the herbivores. Yesterday, Sandy Liebel has shown this in a talk yesterday afternoon, and that the host plants, they are a good driver for predicting the abundance of invasive and non-invasive, of native and non-native species. So let's go to a few figures for the abundance of forest insect invasive species. There are not very many, actually, databases available, but there are a couple, 3 of them actually good. One from Europe, one from continental USA, and one from New Zealand. And they are regularly updated. So here I'll show you the most updated data available. They all refer to trees and woody plants. So that is difficult to separate which of those species are really forest herbivores from those that are taken in and they feed on trees or woody plants that are not necessarily forest species. For the first dataset from Europe was provided by Alain Roch and will be soon made available through the EASIN network. EASIN network is a European Union network for data, biological data. There are more than 500 species of invasive insects, including mites. And I had the dataset from Alain, and I just scored that about under 40 of them are real forest species. There is another dataset from continental USA, accounting for about the same number of species. Maybe now it has increased, 450 or more. for which there are, you can see below, 17%, about 17% having kind of economic impact on forestry. And then the data set from New Zealand, from ECI, that includes more than 250 species. So, which are the major pathways that are associated with the movement of these species? The first one, the most important, is the live plant import. Plants are traded all over the world for a number of reasons. Second is the wood packaging material that is well known to all of you. The third is hitchhiking, species that are occasionally taken with commodities or with travelers. And finally, the intentional introduction for biocontrol. Also here we had a talk 2 days ago, or yesterday morning actually, by Mark Kennis, that was explaining this graph actually, that I don't know, you can see actually the upper line. The upper line is getting up from the 70s or 80s, no? From the beginning of the last century up to the 70s, when there is a big decrease in the number of species that were released for biocontrol, and that is for all sorts of target organisms, agricultural pests, ornamental pests, and so on. Whereas for forest, this is not the case. The decline was not that strong. It remains more or less stable. So why there is such a decrease in the general number of species that are used for biological control? Because of restrictions made by legislation, including the very recent Nagoya Protocol, that is setting some strict limits to the use of non-native organisms for biological control, and also for the fear that those organisms, they may have negative impacts on non-target species in the released habitat. I tried to put together a kind of scheme, I don't know if it is clear enough, about involving 3 trophic levels, the host plant, the herbivore, and the natural enemy of the herbivore, whether they are native or non-native. And there are 8 combinations of both host, herbivore, and natural enemy, and I found a matching for all of them, no surprise. There are so many possibilities that all these different situations can be met. And from the very native one, from the very non-native, so all varieties of combinations are possible. I will look to the same figures for plant pathogens because they have a link with insects, of course, being several insects vectors of facilitating the outbreak of plant pathogens. The data here are for the same, not for the same area, for Europe, continental USA, and for China. And the numbers, they are much more different compared to insects, probably because attention to this kind of approach was lower in the past, but it is increasing. In Europe, there are almost 200 species of forest pathogens that are non-native. In continental USA, about 40, and in China, about 50. But still, the number is underestimated, and also because the hidden nature of many of these pathogens and the effort that has been put in the past to look better into their occurrence. Again, in the same biological invasion special issue, there is a paper identifying the major pathways for plant pathogens. And there is a nice picture that I wanted to show here, which is the map of live plant import. You can see the size of the arrow is proportional to the commercial value of the traded plants. It is impressive to see how many plants are moving around on ways that are really difficult to predict, and that is the major source of problems for plant health. Of course, pathogens, they have also traditional pathways, the wood packing material, like the insects, but they can travel also through wind or water, or they have also animal vectors. And at the end of my talk, I will bring an example about that. The same scheme can be done for an interaction where instead of the natural enemies, we have the symbiont, whether pathogen, bacterium, or virus. And the same situation can be found in the literature. All sorts of combinations are possible. So new associations are continuously made available in different geographic areas. Let me have a short digression into the relationship between insect vectors and plant pathogens, because there will be a talk later today in an entomology session of the meeting at 6 o'clock, where I will present together with Alberto Santini an example about how pathogens, they can be non-native organisms that exploit native systems of other pathogens and vectors to become successful invaders. It will be the case of the elm and the Dutch elm disease, and the case of cypress and the cypress canker. Both systems, they heavily rely on a niche that has been taken by a non-invasive that has replaced invasive that has replaced the non-invasive fungus in the association. Let's go now to climate change. Climate change is a difficult issue when we deal with invasive species. There is not very much information. So I tried to think about which are the possible implications of climate change in the process of biological invasion. Climate change is well known, so I don't have to explain anything. I will explain a little bit what are the effects of climate change on insects in general. What has been produced by a couple of reviews, this is the books on insect outbreaks, the Pedro Barbosa books that were produced in the 80s and then revisited not many years ago, in 2012, where the insects, they may respond to climate directly through direct effect of temperature, or indirectly through the host plant or through the natural enemies. And and we may have temperature or climate, the weather in general will affect both the insects, either herbivore or natural enemies, or the plant. And so the final outcome will result of the combination of the different factors involved in this action. Based on a prediction that we have done when we wrote this chapter, and assuming, giving a different weight to the factors involved, we could come up with a prediction that there could be a positive effect as well as a negative effect on the insect performance, depending on the models, depending on the systems. So it is very difficult to generalize these consequences of climate change, and perhaps we should address things species by species, or at least guild by guild. Most, of course, what I will discuss now will refer to the response to temperature, which is illustrated by that typical relationship, and by the position along the x-axis where we want to set our model. I tried to put here a scheme where the climate change effect on the biological invasion can be set according to the different phases of the biological invasion: before transportation, during the transportation, at arrival, at establishment, and at the spread after the establishment. There are a few things that can be hypothesized. The effect of climate change on pre-transportation, transportation, and arrival. We don't know, we don't have data. Whereas we have a few data for the effect of climate change on establishment and spread. So the first three crosses, they are just to be explored. The other ones, I will talk briefly about them. So I tried to figure out 4 ways through which the effect of climate change can be related to biological invasion. The first one concerns the range expansion or contraction of native species when they are outside of their native range. They are kind of invasive species, very often very close to their native range, because they can be either dispersed naturally, I mean by flight, by movement in any case, or they can be taken by humans outside of their native range. The second point concerns the same thing, range expansion or contraction, but for non-native species, and also in this case, it could be natural spread or human-mediated. The third will address the establishment of the non-native species and how the different climate can affect it. And the fourth, how the population dynamics can respond to the climate change in this new range. The first thing, you know, I worked with processionary moth. That is my basic model for many, many years. And we were able to show that this species is expanding the range outside of the native range naturally and through human-mediated dispersal. So the first scheme on the left is kind of natural spread in the Paris Basin, which is due to favorable conditions for larval performance during winter. Higher temperature, better performance, better survival. The moth is expanding. And the rate is kind of something between 5 and 7 kilometers per year. The second, which is the picture of France with those points in the black area is the area not already invaded by natural spread, but it has been invaded in a punctiform way because humans have taken the processionary moth colonies there inadvertently with transplant of big trees. The moth is spending time as a pupa in the soil, and when they do transplant of big trees with soil, it is very likely that they carry pupae from the nursery to the destination place of the tree. And that has allowed to verify that the climate was suitable for survival even outside of the native range and also outside of the expansion range, which was new to us. Those areas, according to the model, they were not available for colonization, but they became, probably because of climate change. And the last figure is the oak processionary moth. That was another introduction, human-mediated introduction, that is in London a few years ago, where it is a new, completely new problem that's taken in with plants for planting, and the survival was really unexpected under those climate, but actually it did very well. Factors are not completely clear. Why the pine processionary moth in this case, they do very well in the expansion area? This is a very simple model where you see that the flight of the moth during night, they fly only during night, is strongly dependent on temperature. As long as the temperature is above 14 degrees centigrade, they do fly, otherwise they don't. So the number of nights during summer, which potentially useful flight, is very key issue for the dispersal and also for the establishment of the moth in the area. I have another example here for a non-native pest gypsy moth in North America that was introduced a long time ago in Massachusetts, and then it has spread all over the eastern part of USA. And climate change matters because very recently there were Patrick Tobin group provided data about the response of gypsy moth larvae to supra-optimal temperature that is limiting the colonization, not at the colder side, as we have seen for processionary moth, but on the warmer side. So high temperature they are limiting the expansion or the performance of the moth in some parts of the range. And this is another example, also from North America, where the hemlock adagid, which is an introduced pest of hemlock, is just expanding the range to the north because of milder conditions during winter. Still, in the south, the expected retraction has not been observed because the population became locally adapted to the warm conditions in the south, as in a very recent paper published a few months ago. So when we compare the behavior of native and non-native species in relation to climate change, especially in the range expansion, we say that we have examples of species from both categories, and they both respond in the same way, according to the different data. Where it is explained, it means that the mechanism is known. Unexplained has been observed, but we don't know the reasons for that. And then there are papers about modeling, more mechanistic modelings, ecophysiological modeling, very interesting, or envelope modeling just based on the climate matching. There is a tendency for having kind of more frequent prediction about contraction are not met by both native and non-native species. So they do expand to the north, either elevation or latitude, but they do not retract to the south, or they do, but with lower frequency than they do expand. And that is the reason that should be further explored. As far as the rate through which they spread, it is the same. There is no difference. In the new habitat, the non-invasive, they behave like the invasive, they behave like the non-invasive species. The pattern of the rate of spread, they are very similar. So what happens when the species arrive? What is the likelihood of establishment? Is climate in any way responsible for a different probability of establishment? That is a very difficult question, and we have plenty of examples of species from subtropical that are taken to temperate areas, and they do establish, but whether temperature is the limiting factor or other factors are involved, we don't know. This is a paper done by my group on the distribution of non-native species of bark and ambrosia beetle in continental USA, where for each species there was the occurrence at the state level, so we could do a kind of model just to see how these two categories of organisms respond to a number of environmental variables. Now I don't have time to go through, but there's geographic distance, temperature, rainfall, amount of forest area, and amount of trade. And we see that this is the panel is just for non-native species that are not the native one, I didn't put them. Ambrosia beetle, they tend to respond much more to abiotic variables, which is weather, than bark beetles that are more associated with trade, if any association is shown. So temperature and rain especially should be factors that are important for the potential to establish non-native ambrosia beetles in continental USA. Changing weather, changing climate could bring the change also into this pattern. The fourth point addresses the population dynamics, and that is really the most difficult to address. Population dynamics has a huge number of variables involved, and whether the change of the climate could affect all the other variables together, it is very difficult to come up with conclusion. I show here again pine processionary moths in the expansion range in the Alps, before and after the range expansion. So the horizontal red line shows the what was the occurrence of the moths, very low density, before the large outbreak that followed the range expansion and the change of the climate. It was lower, then now it is higher, although fluctuating a lot in both conditions. So are we expecting a shift in the density? Is this shift stable or not? This is a big question mark, and we are just at the beginning of this process. Certainly for other models like mountain pine beetle, Barbara Benz had a talk about that. The pattern is different. The outbreak is still ongoing, still high density, but I think we need more time in order to see what will be the final outcome of this potential effect of climate change. So I'm going to the summary. It's difficult to disentangle factors involved in the response of invasive species to both factors. We know that trade and travel are very important in the early phase of the invasion. We know that climate change can be, because climate change can modify the local condition in the source populations by making insects more abundant and so increasing the probability to be taken up with commodities or plants, whatever. But then climate change is also very important for establishment and for spread. Definitely trade is the driver. There is no question about that. Climate change may contribute. We don't know yet how much, but it could have a weight. Other factors that I will use the last minutes now to talk about could be added. We did a little bit of work in Italy on how non-native species they establish around big ports, so around places where commodities are coming. And we selected 15 major ports in Italy where traps for wood-boring insects, beetles, were deployed, both in ports and in the forest close to the fort, to the town. I mean, usually 10 or less than 10 kilometers. And we surveyed the traps over 3 years, and we found that the richness of non-invasive species is much higher in the forest than in the port. So, and that is quite expected because it is very unlikely that you intercept the insect exactly when they arrive. But if you deploy traps close to, the probability to get them is quite high. And the density of these non-invasive species, if you go far from the port, in natural forest, it is even much lower. So that is a good way, we think, to address the occurrence of these species and to detect their occurrence quite early after the introduction, because intercepting them in the real time when they are introduced, it is very unlikely. Another aspect that could be considered is whether those insects, they carry symbionts with them, and whether those symbionts, they can travel with the insect and with the commodity and being delivered together. We used another set of 3 big ports on which we went to the opposite process. We selected 2 species of one bark beetle, one ambrosia beetle that are most frequently intercepted abroad. So those species that Italy is exporting is one Orthotomicus and the other one is Xyleborus saxazzeni. And they were analyzed for the fungi that they carry on their body. And we found a huge number of species, several tens of species on each organism. Some of them, they were really pathogens that they could travel with them. They can be delivered when they arrive. And whenever they establish new relationship with a local species of native species of bark beetles in the arrival place, it is completely unknown. So, just to conclude, the species pool available for invasion is huge. We don't have a very clear idea about. Yesterday morning there was a session about the sentinel plants, which was interesting, just trying to find out those species that could be introduced, but the number of them is extremely high. There is no saturation in the number of species that have been introduced, so we can expect that this number will increase, and will increase as long as trade will stay high. Very little to do with that. Climate change may help, maybe may help both ways, before the transportation, after the transportation. And invasion patterns, they are more subtle than we should think, because hidden symbionts, they can be taken, which is a kind of side to explore more. And we need action, but which type of action? Of course, biosecurity continuum is an action to survey about all potential things that we can deploy in order to mitigate the process, because there is no other possibility than mitigation. It is almost impossible to stop. And finally, I want to thank my university for giving me the possibility to work in this field. I want to thank also the Italian Plant Health Services. Italian is a black sheep, as you know, in the invasion biology, because it is the place where most of the species are introduced for the first time. There are a number of reasons. But the Italian Plant Health Service, they're doing a lot now. They have taken this task, and we hope that it will go much better in the future, and a few grants that we got from European Union. Thank you.
Thanks very much, Andrea. That was a wonderful presentation, and it was good to be able to see it also. So we have time for questions, and we have a roving microphone over there. So if there are any questions, just raise your hand and don't speak until you have the microphone, because nobody would hear it in this large room. Anyone? Oh, okay.
I'll start with a small question, I guess. The difference between bark beetles and ambrosia beetles that you guys noted in relation to abiotic factors like rainfall and so on, why do you think that is? Do you think it's because the ambrosia beetles, the ambrosia fungi need moisture and the beetles are dependent on those? Or, I mean, some hypotheses.
Yep. This was our hypothesis as well, that moisture, availability of moisture is promoting the fungus development, and so the ambrosia, they develop better. But this is just kind of, hypothesis to test. We found that where moisture, rainfall is higher, is a higher probability to have a non-native ambrosia beetle species. Then the mechanism should be further explored. Maybe there are also other factors explaining that we don't know. The biology of ambrosia beetles, unfortunately, is still not well known as that of bark beetles. Yeah.
Come on.
So thank you for your presentation. I kind of wonder if spatial scales matter. For example, for the hemlock woolly adelgid in the southeastern US, we're finding that elevation is important. So insects that are at the lower elevation, that are experiencing high temperatures during the summer estivation, are showing greater mortality than the ones at the higher elevation. So maybe at a smaller spatial scale, we may not see range contractions, but we may see some sort of a negative effect of warming temperatures in this instance on some of the non-native insects.
Yeah. Thank you. Yes, where you have a steep elevation gradient, like in the mountains, or you have a low elevation and medium and high elevation on a short distance, most insects, they move very easily they can move quickly among different habitats. And so they can try to address the problem in this way. This is a typical for the Norway spruce bark beetle in the Alps, whereas the outbreak, they start at a low elevation, and then they move up as long as conditions of temperature becomes more suitable. Certainly, if there is a retraction, it should be expected at a low elevation in the warmer sites. And this is what has been observed for a few species. For example, if you look for the pine processionary moth in the northern Africa, where they are challenging the surviving relic stands of cedar, native cedar, the processionary moth has moved from the Aleppo pine plantation in the low elevation to the upper mountains where they defoliate the cedar forest. And so, interestingly, the pines are not any longer affected by the insect because it's too hot for the insect, whereas it has moved to upper elevation, threatening actually the survival of these native cedar stands and implying a lot of cost and management for foresters. Hervé?
Hervé, wait for the microphone.
Yes, Andrea, don't you think that climate change has also an effect on during the transport phase? Because, for example, the Arctic route is opening and people are exchanging more wood as a biofuel right now. So there might be an effect of climate warming also during the transport of the invasive species.
Yeah. Yeah, this is a good observation because transportation can be done in different ways by different carriage, and depending on the conditions to which the insects or the organisms are exposed can be very important for their survival. I will bring a very short example that is nothing to do with forest, but do you know that the African malaria was found a case in Italy just 1 month ago? A child died of that, and the most likely hypothesis was that it was a malaria mosquito, Aedes gambiae, taken with luggage from Africa by travelers, and that survived in the luggage. So these are the things that we are very, very difficult to predict, very difficult to take care of, but they could happen, definitely.
Okay, I think maybe we wrap it up here, so please join me in thanking Andrea for his wonderful presentation. So we have another speaker, and so you're all welcome to stay. I'm sure it will be just as fascinating. And so this next presentation will be by Professor William Manning. He's an emeritus professor at the University of Amherst in the United States, and you're really welcome to stay. Bill has made an enormous contribution to the science of air pollution and climate change impacts on forest ecosystems. And his studies were critical to untangling the so-called Waldsterben, or forest dieback, that was observed in the Black Forest and elsewhere in the 1980s, or since the 1980s. Bill was also the editor of the journal Environmental Pollution for about 30 years. And he's been an inspiring mentor to many. And when Bill retired 2 years ago, the research group Air Pollution and Climate Change created the Bill Manning Award for the best poster presentation at its biennial conference. So given his experience, Bill is the most suited scientist to talk about the history of air pollution and forests, from forest dieback to climate change. And I see we have your presentation. So over to you, Bill.
Thank you for that introduction. I'm very pleased to be here today to help you celebrate the 125th anniversary of the IUFRO and the members' contributions to science and society. It is quite an accomplishment. I'm glad to be here. My title has somewhat changed since my abstract, because I realized that air pollution didn't really begin in 1750, maybe 1751, 1748, but it really didn't start then. That's when most people put in their papers, starting with the Industrial Revolution, da-da-da-da. That's not true. Air pollution has been with us since the first human being learned how to start a fire, and then learned how to manage fire. And that technology, the first technology for human beings, is still with us today. It's our major technology for energy and transportation. So, it didn't begin then. You've introduced me, but my co-author needs some introduction. Elena Paoletti is well known to everyone, I'm sure. I see her as the spirit of the IUFRO, the new IUFRO. I've been pleased to be her collaborator for a number of years. It's very helpful and useful. So when she suggested this topic to me, I said, yes, history would be important for an anniversary celebrating history. And also she probably felt I was here for most of that history, so that I could do that. But anyway, we learn from history. We like to know where we came from, what happened, how does that influence where we are now? Does it affect our future? Have we ever learned anything from history? So it's important for history for a number of reasons to do this. History may not have been your favorite subject in school. It is for not for most people, learning dates and things like this, and kings and queens and so on. It's just not all exciting. But I hope today I can make history a little more interesting for you. So I'm going to do that with a series of slides. And this is the first one. Air pollution did not begin with the Industrial Revolution in 1750. Early people learned how to use fire. They did it because they were cold, for one thing, and they were hungry. They wanted to be warm, and they wanted to cook their food. If you cook food, it's more nutritious, it's easier to eat, and that's how human populations got started. Better nutrition, better survival, being warm. They also learned how to get rid of their waste. They began to use settlements, so they had to get rid of waste and dispose of waste. And they became involved in mining and metal smelting activities to make weapons and other things, tools. They began by burning wood. The wood they burned contained carbon that had been fixed within previous time. That was fine because they were returning that carbon back to the atmosphere. But they began moving then into peat and eventually into coal. That's carbon, that's ancient carbon, which was not being returned from where it came. So it's been estimated that human activity polluted the air in Europe over the last 2,000 years, probably before that, mostly through metal smelting. The Romans were very good at working with lead and silver and other people, and so pollution goes back at least 2,000 years. This is a nice little plate of the Industrial Revolution. In the upper left-hand corner, you can see that life, this is primarily in England and Western Europe, that life was simple and pastoral, based on crafts, self-sufficiency, and a small population living in a village. But the development of industrialization and factories meant, on the upper right-hand side, large cities developed, and point source pollution on a large scale began to emerge. And the vegetation in the vicinity of all this also was affected. You can see in the leaf there's some acute sulfur dioxide intra and red alder. And if you carry that further along, you have forest decline developing. But on the left side, there were profound social changes. Life was never the same. and life has never been the same since. This is when the work ethic developed, when you had to go to work. Someone else told you what to do. Your life was never your own. So the boys in the center there are learning how to mine coal, a wonderful apprenticeship program. Don't they look very happy? They're delighted to learn how to mine coal. And the women below are just as happy to work in factories, aren't they? You see the expressions of exquisite joy? So life changed because of fire. Everything has changed because of fire. And our whole society is based on using fire. So let's talk about fire for a little bit, combustion, because combustion is the principal problem of our atmospheric conditions today. It's all down to combustion and fire. We burn things. There's a lot of interest in using methane or natural gas as the clean fuel to get away from oil and coal. So if you use methane, you can have complete combustion. And if you look at this slide, you can see that with adequate oxygen and light, you get heat and light as a product, but you also get warmth. And the bottom line is that you get carbon dioxide and water vapor from complete combustion. This is great. This is why it's called a clean, desirable fuel. But carbon dioxide and water vapor are major positive climate forcers. So maybe this isn't such a good deal after all. Most of the time, we have incomplete combustion. Things don't burn cleanly. If you have a fireplace, you know that wood smoke is not a product of clean combustion. Oil, coal, gasoline, diesel, wood, peat, biofuels, crop residues, anything we can burn, we burn, get rid of and use. From that we get carbon dioxide, carbon monoxide, soot, suspended particulates, pHs, and a whole host of organic compounds, many of which are toxic. Water vapor, small hydrocarbons, volatile organic compounds. This is interesting because VOCs can feed right into the photochemical oxidant cycle that produces ozone. Sulfur dioxide, SO2, and sulfuric acid. There's a whole litany of these things. Oxides of nitrogen, NO, NO2, which are also involved in the photochemical oxidant cycle, and lots of metals. So incomplete combustion is dirty. This, of course, with the development of industrial production, led to acidic deposition. If you keep putting stuff in the air, eventually it has some effect. So the products of the Industrial Revolution are things called wet deposition, rain and snow and fog, acids like sulfuric acid and nitric acid, dry deposition of particles, soots, gases, and all sorts of things. And the first use of acid rain, it turns out, was used in 1870s by Angus Smith in Birmingham. Birmingham, a center of early industrialization and a center of intense acidic deposition. So what did the result from all this? Other than unhappy factory workers, we had forest declines, interactions of pollution and natural causes. This, all over the world, there were serious and extensive forest declines, all over the place. And anytime there's a disaster like this, it's a tremendous stimulus to research. And all kinds of people, from soil scientists to atmospheric chemists, to biologists, to entomologists, to pathologists, everyone got involved in this. So in many ways, it was a great learning experience. It wasn't too good for the trees, but it was a great learning experience. So the forests were exposed to a variety of things: direct exposure to gases, SO2, ozone, hydrogen fluoride, others, acids like sulfuric acid and nitric acid, and particulates of sulfur and nitrogen. Indirect exposure to soil acidification, nutrient leaching, magnesium and aluminum solubility, and all interacting with natural causes like drought, frost, insects, and diseases. So each group had its own champion, its own idea of what was going on, And so this spurred all kinds of research. And eventually, I think it became evident that it really was an interaction of both natural and acidic factors. But it was a great learning experience. And then it went away. Why did it go away? Why isn't it here now? This is an example of somewhere in Germany, what it looked like, if you haven't seen it, and also in the Czech Republic. Here's an interesting picture. When we have problems like climate change, global warming, acidic deposition, etc., we use them as blanket terms to cover all occasions. This is the destruction of Fraser fir on Mount Mitchell in North Carolina in the United States in the 1980s. On the front page of the New York Times, above the fold, on the front page, was a beautiful picture of this, similar to this, saying, "These trees were killed by acid rain." Everyone was saying, "Oh my God, the trees are dying from acid rain." The New York Times said it was so. Did the New York Times reporter do any investigation? Not really. If he had, or she had, they found out these trees were killed by the woolly adelgid, an insect. The previous speaker was referring to the woolly adelgid and change in temperature. This is forest decline, has nothing to do with acidic deposition. So I think we have to be very careful how we define things and look at things. And using blanket terms is real easy, but not necessarily accurate. So at the same time, because of incomplete combustion and very few controls on incomplete combustion, the products of incomplete combustion, the photochemical oxidant cycle became very active with inputs of NO and NO2 and small hydrocarbons and ultraviolet radiation. And in Southern California, for example, the ponderosa and Jeffrey pines began to decline and die in large numbers. And if you look carefully at the needle pictures on the upper, on the upper left-hand side, you can see that the area around the stomata are yellow because the tissue's been damaged, and in the next frame, the older needles are falling off. They're supposed to be retained, they're declining and disappearing. In the picture on the right-hand side, you can see various stages of decline and death caused by ozone and drought, and also from predisposing these trees to root disease and bark beetles. So it's a complex. It's not just ozone killing the trees, it's ozone predisposition together with drought, root diseases, and bark beetles. The most interesting part of this thing, though, is the lower right-hand corner, left-hand corner. There's a graph of ozone concentrations at that time. And if you look on the far left on the top, you can see what the highest peak concentration of ozone was in Southern California. I can't see it that clearly from here. In 1955 was 60 ppm, not ppb. That's terrible. So that's where we were by following our new technology. We're in love with the technology of fire and combustion, and that's where we got to in 1955 in Southern California. So eventually government had to do something. People were complaining, people were agitating. What are we going to do here? This can't continue. People were dying in Southern California. People were getting asthma, all sorts of things. There were epidemics of smoke pollution in London and Denora, Pennsylvania, and ozone and peroxyacyl nitrate in Southern California, acidic deposition, forest collapse. The whole world was going down the drain. So government had to act. Governments act slowly, usually, slowly and only with prodding. So some Clean Air Acts began in the UK in 1956, in the USA in 1970, and people began to realize that maybe we should be moving to cleaner fuels as a result. So it also was discovered at this time, if you took aerial photographs, high elevation aerial photographs, that the atmosphere was in a condition called dimming, not as bright as it should be. And this is because of all the aerosols, primarily sulfate aerosol, in the atmosphere. reflecting light back to space. Now, unfortunately, there are a number of people right now whose response to a band-aid approach to climate change is, global warming is, to artificially generate inert aerosols and release them to do the same thing. I hope they're not successful. So anyway, what happened was that visibility was lower, and if you remove that, in this slide next to it, you reduce haze, fog, mists, and low clouds. Some of those mists and low clouds were acidic. So let's look at dimming and brightening a little, because it relates to global warming and climate change a lot. Sulfate aerosols and dimming. This relates to how this affected photosynthesis in the land carbon sink. Sulfate aerosols reflect sunlight back to space. This is good if you want to keep your temperatures down and the light down. But it resulted in a very uniform diffuse radiation, which, according to estimates, increased land carbon sink by 25% from 1960 to 1999. 1960 to 1999, a 25% increase in land carbon sink. If you remove the dimming, or I'm sorry, I'm ahead of myself. This resulted in a more uniform light distribution within the whole canopy of trees. If you remove that, you increase light and you increase PAR and you increase photosynthesis. But most of the illumination is now limited to the top of the canopy, not distributed uniformly within the canopy as before. And also, some of the leaves at the top of the canopy will be light saturated. So the question is, are aerosols good or not? So global brightening was a result of the Clean Air Acts. Do you know the law of unintended consequences? Be careful what you wish for. We got clean air. Clean air means that less light is reflected back to space. This means that temperatures are warmer. It means that changes in growing seasons and growth can happen. There are influences on insects, pathogens, and invasive species. There's increased respiration and water use by plants and possible drought, and there's a whole category list of things, other things that might happen. So, clean air, global brightening, warmer temperatures. This led us to the greenhouse effect, because the global dimming was masking global warming until the early 1990s. It was there. It's been there since the beginning of the Industrial Revolution. We began polluting the atmosphere in 1750, and this continued ever since. And so if we have aerosols in the air reflecting light back, we have cooler temperatures. So now we have warmer temperatures, especially at night. And the cast of characters for this now are water vapor, which is probably the most important radiative forcer, but it's not present all the time. But the one that's found all the time is carbon dioxide. Carbon dioxide is the poster child for global warming. That's all you hear about. That's because carbon dioxide is present all the time, never goes away. It also is the major contributor then to global warming. Ozone, methane, nitric oxide, and a whole cast of synthetics which won't disappear for probably 100,000 years. So we have changes in precipitation and temperature. This is all affecting forest. I am actually still talking about forest. Changes in precipitation and temperature, drought, range changes, fire, insects, diseases, extreme events, phenology, and so on. Elevated CO2 affects transpiration and evaporative cooling. One of the principal benefits of forests is evaporative cooling and participating in the hydrology cycle, which regulates temperature in the atmosphere. So if we're reducing evaporative cooling, we have a problem there. Left to its own devices, the forests and the oceans nicely regulate carbon dioxide and temperature. They don't do that anymore because the amount of CO2 we're putting in the air, anthropogenic CO2, is greater than either sink can handle. So 40% of it is still floating around and will be with us for 1,000, 10,000 years. Ozone and carbon in the forest. Ozone gets overlooked. Ozone is a very potent forcer, but it's short-lived. It's only involved in the growing season. It doesn't last very long. But as forests are the second most important carbon sink, current ozone concentrations, even at lower levels now that we have Clean Air Act, cause chronic changes. It affects stromal conductance, photosynthesis, biomass, net production, and it also, if water availability is there in the future, it may increase changes as well. Elevated ozone could limit or negate positive environmental carbon dioxide effects on vegetation. What we need are criteria for tree selection for planted forests, but trees are more responsive to these changes than the ones we have now. Carbon in the forest. Everything we know about global change, climate change, global warming, almost everything we know comes from modeled predictions. Very little comes from experiments because it's extremely difficult to do meaningful large-scale experiments with trees of any size. So a lot of what we have are called predictions. They're not necessarily establishment. Carbon dioxide has increased 144% since the Industrial Revolution. It's now at 400 ppm plus. You can look at this every day if you want to by going online to something called CO2 Daily. It'll tell you that day what the carbon dioxide content, it'll tell you what it was the previous year, previous day. If you want to get really involved in carbon dioxide, you can do that. Carbon dioxide, CO2 and nitrogen deposition increase growth. The role of other factors is not very well understood, ozone and other factors. What is interesting is the assumption is the elevated carbon dioxide increases growth, and this is good, it will continue forever, and that's the way it's going to be. There's some evidence now of slowing of the forest biomass carbon sink. Some evidence from Europe due to land use and disturbances resulting in stem volume decreases as well. So the forests are not going to do this forever, and nor are the oceans. I consider carbon dioxide to be an air pollutant because it exceeds what it should be if it was cared for by the oceans and the forests, and it has adverse effects. So to me, this is a total air pollution project. Global temperatures. Global temperatures. The last 3 years have had record high temperatures. Now, these are global averages. Global averages sound very small. 1 degree Celsius, 1.5 degrees Celsius, 2 degrees. What is that? Very low. But that's it for the whole globe, the whole planet. It's not the same everywhere. For 3 consecutive years now, we've had high concentrations, plus we've had the influence of El Nino on this. Global average temperatures have increased at least 1 degree Celsius, and it is not likely that these high temperatures would have occurred without our involvement, without human influence. This is not normal variation. This is not something to do with sunspots and the rotation of the globe and things like this. This is down to us. So, I have a bit of time left. That's where we are. That's where we came from. This is history. Where may we be going? I can see the interaction of stresses and disturbances with climate variables and with climate forcers. I see possible future changes affecting forests by increasing atmospheric carbon dioxide. It is not declining, it is decreasing, continues to increase slowly. Increases look small, 2 ppm, what's that? 4 ppm. Well, the other thing I digress a little bit to say is that the other thing that's happening is that there's the summer-winter oscillation in carbon dioxide concentrations in the air. In the summer, the concentrations go down because forest vegetation, other vegetation is taking up CO2. In the winter, they go up because the vegetation isn't there in the northern hemisphere, and it goes up. But there's a shift that happens which indicates that the strength of that change makes a big difference in CO2 concentration. So what some people are suggesting now is that the change in the winter one is not as what it used to be. It's beginning to change somewhat, indicating that the summer sink isn't working very well. So anyway, changes in precipitation patterns, possible drought, decreased, a whole litany of things here, decreased transpiration, net productivity, atmospheric cooling. Atmospheric cooling is the key to this as far as forests are concerned. Fires and climate, forest disturbances, CO2 release, changes in forest species and compositions. Where I live, people like to look at the fall color change in sugar maple, Acer saccharum. The projection is that beyond my lifetime, that maybe there'll be other trees there that aren't so interesting in the future because rising temperatures and changes in hydrology may make it not possible for the. So are we planting the right trees, the right places, for the right purpose? I don't know. So I probably talked too fast, but there it is. And this is what we'd like to see in the future. Thank you.
Thanks very much. We have plenty of time for questions. And again, if you just raise your hand and wait for the microphone. Here.
Okay. Thank you, Bill, for this great presentation. I would like to know your vision or your opinion about what are what is the best and the most cost-effective way or solution to reduce the air pollution in city, in particular focus on the increasing surface ozone levels in cities.
I'm having trouble following you, Pierre. Could you speak a little louder?
Okay.
Sorry.
I would like to know your vision, your opinion about the possible cost-effective solution to reduce the air pollution in cities, in particular for the increasing surface ozone levels in cities. For example, I don't know, what about the urban forests? What about the green infrastructures or other technical ways? I don't know.
Elena, can you help me? I'm having trouble understanding Pierre.
So the question was what could be done to improve air pollution in cities and what may be the most effective method and most cost-effective method to do that. And perhaps, were you thinking of involving trees in that also? Right.
There is a great deal of interest in using trees in cities to reduce air pollution, particularly particulate air pollution. This is helpful there are probably often not enough of them to make a real difference. The other problem is if they're planted very intensely, they tend to trap pollutants rather than disperse them. So it depends on how they're configured and what the prevailing wind patterns are in the city. There's, I forget the name of the city in Europe, has long axes coming into the city, of long axes of avenues, and so the wind is moving along the axes. If you plant trees along those axes, it helps to carry pollutants away. But if you plant a whole forest along there, it simply traps it. So I'm not sure there are enough trees to actually make a very large difference. Is that your question?
So I understand
Sure.
that pines, for example, with many needles can have this filtering function, and that they absorb particulate, for example, but perhaps also trap other.
Right. If the leaves have hairs, if they're hirsute, or they're hairs, that's helpful in trapping particulates. The difficulty there is if it rains and the particulates are soluble, they go on down into the soil. And so if it's metals or something like this, they could end up being built up. I think trees also have a certain aesthetic value and also try to relate people back to the nature which they've since lost contact with. People who live in cities, it's important to have them involved with trees. I think there's a lot of psychological values. People feel reassured in areas with trees. They feel more relaxed, they're more comfortable. Sociologically, a lot of benefits. But in terms of pollution abatement, I don't think that this really is a major factor.
Thank you.
Thank you. Is there another question? Oh yeah, several.
Thank you very much for the great presentation. I have a question about, actually, we accumulate many knowledges about the effects of air pollution from the experimental studies, but always we have problems with how to scale up or how to apply these results to real forests. So what is your opinion or suggestion to solve these problems?
Extrapolation has been the bane of science since it began. It's difficult to move from experimental studies to the larger environment. It is done because that's what we can do. And it's best if people who do modeling take that empirical data and try and incorporate it into their models. But you really, it's a bit dangerous actually, because when you read the titles of journal articles, and they'll say to you that this is this and that's that, and then you trace back how it was done, and they say about, forests will respond this way. It's either done with empirical evidence, which can't be extrapolated, or some modeling, which doesn't really relate. So it's difficult to take that data. What you're learning about it is what you learn from those experiments, how plants function, how they respond, what they're likely to do, how they could behave, but you don't really learn how that 100-year-old oak tree out here is doing very well. That's the problem, is how to extrapolate from there to there. Doesn't mean it shouldn't do the work. It's all we can do. Thank you for your question.
Thank you very much.
Thank you very much, Professor Manning. Very informative presentation. My question relates also to Dr. Hoshika. Basically, the most knowledge nowadays is accumulated from short-term studies or with seedlings and so on. The problem is that the adaptation is not considered. And so my question is, do you think the impact of, let's say, ozone, which is predicted, is overestimated compared to what should be? And also, we don't know, I think, what is how much is plasticity, and when the plasticity stop, and when the injury really start and remains there. So what is your opinion on that?
Genius, I think you're on dangerous ground. If you do an experiment, the objective is to get results. And not very many people are fond of negative results or no results. So the way you get results with a toxicant is to do a dose-response curve. And at the lower part of the curve, you either have a little hormetic effect, or at some point you get a breaking point where negativity sets in. And then you have to decide, what does that mean in relation to what's going on out here? And the chances are very good that you're working under ideal conditions, ideal humidity, ideal soil moisture, ideal light condition, ideal fertilization, that they don't relate very well, because what you're doing is predictive work. All work in chambers and apparatus is predictive. And that's good. We need to know what predictions are. But it is not, this is the argument that's been going on for 30 years. It's not really immediately relevant. But it says this is what would happen under these conditions, and it's perfectly valid science. It's good science, it should be done. But if you're a policymaker, you'd be very frustrated with this. Good question.
I have a question.
Sure.
In our business meeting yesterday, there was a fair bit of discussion that we should have more interaction and more consideration between pathology and entomology. And in your talk, you mentioned the woolly adelgid, and that initially it was mistaken for forest dieback due to air pollution. And so I'm just wondering, like, do you think there's enough awareness among the forest health community of what is due to disease, insect impacts, air pollution, climate change, but also the interactions, I believe. I mean, there are multiple factors, and so it's quite possible that sometimes there may be interactions like air pollution, climate change impacts, increasing the susceptibility to insects or pathogens. Should we expand our horizon and look into this more?
It would be nice if you could put together a consortium of people to do this. What you're saying is that, yes, all of these factors are involved, but it's difficult for many people to study more than one at a time or two at a time. So if you had a consortium of people doing the same thing, it'd be very helpful. Yes, the closest thing I can think of with this is the Aspen Face project in Wisconsin. I don't know if you're familiar with that. It was the world's largest air pollution experiment with trees. Now, admittedly, trees were not, large trees. They were 3 or 4 years. I've replicated 12 open-top chambers, enormous ones with both carbon dioxide and ozone, and different tree varieties. And then a lot of people were brought into this with their own specialization, including entomologists, mycorrhizae people, all sorts of people got involved in this because they were invited to be involved. They didn't initiate the experiment. David Karnofsky did. But then he said, look, here's this huge experiment. It's costing a fortune. Come and join. And so the number of papers came out of that increased exponentially. So that's the only example I can think of. But it's hard to find funding to do that, people who want to do it. A lot of people are some people are more interested in their own work than anyone else's. And so why would you want to talk to an entomologist or a pathologist or a physiologist or a statistician or a modeler? Why would you want to do that? You've got your thing. So I think your point is well taken, that there has to be some way to persuade people, to encourage people. Maybe the IUFRO could be very useful in doing this, because you represent all kinds of disciplines, and maybe a good project to look at the IUFRO interactive project. Sounds good to me.
I like that idea.
Yeah.
Elena, we should pursue that further. Any other questions? We could take another one. Way up in the back there.
Way up in the skybox. How do students deal with this? With your 600 people in here, your lecture, how do they?
Hello, and thank you. I have a question. So, given times of declining budgets, limited capacity and capabilities to really manage forests and manage things the way we'd like to, between invasive species, climate change, air pollution, all of these factors that are contributing to declines in forest health, where do we get the most bang for our buck? What do we do? What do we focus on?
Well, this is not really my area, but what I would do if I had the controls, I would select in, say, Europe, North America, and Asia, and wherever else, a representative, relatively unmanipulated forest, if I could find one, and I put together a group of people at each site, and I say, this is what we're going to do. We're all going to study this, and we're going to study whatever we decide we're going to study uniformly, and we're going to do it for 10 years. And we'll get our governments to pay for it, or the UN, or somebody could pay for it. I don't care who pays for it. And then we would learn something. I think one thing about a state deposition, but I think foresters learned what a forest was and how to manage one and how it worked. That's what I think they learned. And we could do the same thing now with global warming and climate change and air pollution and invasives, and just do it. It could work at all. We could work from the molecular level to the descriptive level to the modeling level to the predicting level. Whatever you decided to do, that's what I would, in an ideal world, that's what I would do. It's time to start looking. If you can't describe a problem, then you don't understand the problem.
So do you think we need to do more research first and understand better what's going on, or are we in a position that we could also look at recommending solutions? And
I think some things, research has to continue because, you know, research is a search for truth and that changes all the time. So I think that to be reputable and to be recognized as players at the table, you have to say something now, but you have to say it in one voice if you can. And if you look at the literature, there are lots of voices and they say different things. I mean, a lot of what I showed you is some different voices. But for example, is it a good idea to continue to plant Norway spruce in Europe?
it's native here.
Well, I mean, I know I've just committed the mortal sin of forestry, but, you know, do we want to look at different ideas of how to manage? Should forests be managed? Are plantation forests the answer? If so, what kind of trees? There's any number of things that you all know about that you could you know, the insect world, you've already have this. And I think if you don't say anything, then people think you're not doing anything important, and you're watching other people eat your lunch, and so why don't you get at the table and eat some lunch too? I mean, I think you need to start. And I think some kind of a position paper, even if it's sort of mild, it says, we, the undersigned, believe, you know, and you should be this, because if you're not known, nobody's going to ask you, and you know, the IPCC runs mostly by physical scientists and atmospheric chemists and atmospheric modelers. They don't know anything about biology, so you need to tell them. I mean, some of the stuff they come up with is absolutely ridiculous. So, I mean, they've decided that reforestation is going to save the world. Is it going to save the world? I don't think so. So, what are your thoughts? What are your, you know, you have a voice. You're scientists. You need to take positions. People don't want to do that. Oh, it'll be politics, you know, so on. So we don't want to take a position. If you don't take it, somebody will take it, and you won't be heard. That's my feeling. That you know, if you have something to say, fine. If you don't, you know. But you also would have to get together and say, what do we want to say? That would be where you could have a nice workshop somewhere, get away from everything for 2 or 3 days, a nice location, get rid of the iPhones and all this other stuff, and sit down and say, what do we know? What do we need? What can we say? What positions can we take? Is the UFRO important, or is UFRO just a group that gets together every couple of years and has a good time? And really, you know, what do you got to offer? That's what I'm saying. I'm not a UFRO member, so I can say this.
Well, I believe that we do have an impact. Many of our members publish a lot and inform policy, so I think it's slightly more rosy.
Publishing doesn't do it. You and I read papers, they don't. Policymakers don't read papers.
Well, there are policy papers also. So, but I do agree, like, there is the gap to bridge between science and policy, and so that's probably an area that we need to engage more in.
Scientists are always reluctant and reticent to get involved in anything besides their work.
Yeah.
Because they don't want to be known as a grandstander or an ego trip person, you know, one of these people on TV all the time. They don't want to do that, so they just... Anyway.
Okay, so we've just come to the end of the session. It's 3 o'clock, so please join me in thanking again Bill and Andrea.